So funny. It's a lot. Welcome, everybody. This is our first brown bag of the season. We have 28 people online, so although there's just a few of us here, you have a big online draw.
Okay.
So we often expect that at the beginning of the semester because towards the end of the semester, we get a lot of students sitting around the room getting extra credit. So we're going to start by introducing ourselves. I'm Claire Zucker. I'm the Associate Director here at the Water Resources Research Center, and we will be introducing you at length in a minute.
Okay. Henry Johnstone. Yeah.
Robert Vilacek, I'm an energy efficiency consultant and member of the Tucson Commission on Climate, Energy, and Sustainability.
I'm Carl Schmozel. I'm with the Plant Science Department at the U of A.
Mike Herman with Planning, Design, and Construction, U of A.
Robert Rosenberg with the Flint Hills Renewable Energy and Efficiency Co-op, Freaks, in Kansas. We install solar for free.
I'm Brian Capadia. I'm new to town, but I came from New York. I was in investment banking and management consulting, and I've been invited as a judge in the business school, but I'm looking to get more involved in professional career, something to do with nature, engineering, and everything that this beautiful region has to offer. So I'm looking to pick your brains in the near future. Thank you.
Thank you. Thanks for joining us. First of all, I would like to ask you to turn your cell phones off if you haven't, and be sure to sign in if you haven't done that. I also want you to be aware that we have on February 13th, which is the Thursday before Valentine's Day, we have something called the Chocolate Fest here, and we all talk. And this year, we're honoring the flowing Santa Cruz River. So we're going to have a few comments from people about what that's meant to them. And basically, there's just awesome treats. So it's totally worth coming in
for that.
and hanging out with us water people.
What time would that be?
It's at 3:30, and there's a flyer, a red flyer over there. We have our conference coming up in the end of March, and that's going to be a great event this year. It's looking back and forward from the Groundwater Management Act and then forward to the future. And let's see, what else do I want to mention? Looking through all of these things, I think that's about it. We are recording a PowerPoint. It will be presented. It will be on our online site if you would like to see it in the future. Hello, would you like to introduce yourself? We've already all done it.
That allows me to go ahead.
Thank you. I'm here to introduce Henry Johnstone. I'm going to read a little short bio about you. He moved to Arizona in the late 1970s to pursue an interest in active solar energy systems at the University of Arizona, which culminated in a study of salt gradient thermal ponds. Did I say it? Salt gradient solar thermal ponds at the Solar Energy Research Institute in Golden, Colorado. His 33-year career in mechanical engineering began at GLHN, a Tucson-based architectural engineering consulting firm. He was the principal in charge and mechanical engineer of record for the award-winning Arizona Environmental and Natural Resources building, ENR2, as we were just discussing. So today he's going to be talking about energy, water, and air conditioning.
Yes.
Nexus. So thank you.
Yeah, very good. Thank you. Well, thanks for the opportunity to speak here. I feel kind of honored to speak to water people. I think as you'll see as I go through this, I have a completely different bent, maybe spin on water. I think about it in a somewhat different way, I think, from the way you folks generally consider water. But it's an essential piece of the work that I do. So I'm a mechanical engineer, and my field really is in buildings and urban scale energy. We were involved in the ENR2 building, which is a very high performance, low water use, low energy use building recently built on the campus of the U of A. And that was a way to kind of hone some skills on current technology in energy and water and improve kind of the baseline performance metrics for a place like the University of Arizona. That building has a lower energy and water use than just about anything else on campus, and maybe that will set a standard that the university will pursue as time goes on. Our firm, GLHN, has been around for 57 years. We started as one architect and one mechanical engineer, Finnickel and Dombrowski, back in the 60s. We've now grown to be a multidiscipline firm, so we've got architects, mechanical, civil, electrical engineers all working together. Most of what we do is buildings and campuses, and by campus it's sort of a hospital would be a campus setting, a university or community college kind of a thing. And we also do district projects for municipalities. We've been involved, City of Tucson, the kind of downtown convention center district, and we'll talk a little about that in a bit. Yeah, my topic here, energy, water, air conditioning. The energy water nexus is a well-known kind of buzzword, but from my angle, what really matters here is energy, water, and air conditioning. And this is really important in our kind of region, maybe not so important in a place that doesn't have as many cooling degree days as we do, but in southern Arizona, we have a combination of very dry conditions and very high ambient temperatures in the summer. And the reality is it takes mechanical air conditioning to drive the economy. We simply couldn't exist at the scale that we exist now in Tucson without mechanical air conditioning. And so I'm going to just really talk about the water impacts on that aspect of our reality. So I'm breaking this up into energy, water, and air conditioning. So there's three basic topics here. Here's my energy topic. All right, so the first slide here, this was published in 1897. This is a diagram of how a conventional power plant works, although it was originally a diagram prepared by this gentleman, Rial Sankey, a mechanical engineer. Actually, he was a military engineer in the Irish Army. But he became kind of passionate about mechanical engineering at the time when generation of electricity through power plants was just beginning. So he was one of the sort of forefathers of how do we build central station power plants. This is actually a diagram of a pump, but it's a steam powered pump, and it shows the same principles that I want to talk about as we go on in energy production. So this is a Sankey diagram. Guy's named Sankey created a thing what's called a Sankey diagram. You'll see a bunch of these through the course of this presentation. The key thing about the Sankey diagram is the width of the line scales directly with the number of units that we're considering here. So in this case, we're looking at BTUs, thermal energy units here, and the widths of these lines all represent sort of the embedded or embodied BTUs in that particular flow. This is an energy flow diagram. We're starting here at the fire grate. This is where the chemical energy that's in the coal, for example, if that's what this was, gets consumed. The coal gets ignited. That energy is released. The magnitude of that energy is shown by the width of this line here. So you're seeing here the conversion of coal energy into steam energy. You can look at the scale of that line. Well, that's the number of BTUs we now have within the steam. The steam then runs through a pipe and gets to the engine. At the engine, it splits into two pieces. One is the actual work. This is driving the shaft. This is making the pump spin. This is actually doing the physics of work. The rest, and that's this width of this line. The rest of this line is the energy that goes out the condenser. This is the energy we have to basically waste out of the process in order to be able to recycle the flow. So in order to recycle this feed water back into the loop here, we've got to condense a lot of energy here. So the basic process, high pressure, high temperature steam expands through an engine, creates work, and then you're left with low pressure, large volume of steam, and you've got to convert that back into water, done with a condenser. And in this little diagram, this was sort of the theoretical in 1897. This was what the numbers would tell you a process should do. up on top, he actually instrumented this pump and came up with, well, here's the difference between ideal and reality. And sure, there's a lot of losses that aren't in the theoretical that do show up in reality. So that was 1897. Now I just took that diagram, kind of turned it on its side for the purpose of kind of demonstrating how that is relevant to what I'm talking about next, which is how do we make electricity? What's the most common way of making electricity, historically at any rate? And that's through the Rankine cycle. So that's a process by which we operate a boiler. Generally, this is coal, but it could be natural gas. It could also be uranium. This could be a boiler that's running on nuclear power. But we're making this heat, we're making this high temperature, high pressure steam. It expands through a generator here. As it's expanding, it's creating the work that drives the shaft that makes the generator, makes electricity. Then we've got low pressure, low temperature steam coming out of here, kind of woofing out of the back end of the generator here. And we have to condense that back into liquid so that we can pump liquid back down to the boiler here. How do we do that? Generally speaking, at least in the West, we do that with a cooling tower here. If you're next to the coast, for example, you might not use a cooling tower. You might just pump seawater through this condenser because you got a huge body of cool water, and well, we'll just heat it up some infinitesimal fraction of a degree of temperature, and we'll pump it back out to sea. Often in rivers, you'll take a river and run river water through your condenser, which isn't evaporating the water, but it's adding some temperature to it, having a little bit of an environmental impact. Here in the West, though, almost all of our power plants are running with cooling towers. So we're taking a water source and evaporating it using the latent heat of evaporation in water, 1,000 BTUs a pound. We're able to pretty cost effectively convert water into the energy needed that we need to extract from the condenser. So that's kind of what that process looks like from a component standpoint. And this is what it looks like if you do a Sankey diagram of the same thing. So I'm just trying to show my own version of this diagram done in 1897. This is kind of my take on how that it looks now for a fairly typical power plant of the type that DEP operates up in Springerville or the Four Corners. They're up on the Colorado River. A number of these are around. Coal comes into the boiler here. I'm showing 87 megawatts. Again, that's kind of the energy that's embodied in the coal that gets shoveled into the back of this boiler here. The process goes through here. So we've got the coal energy here. Here's the split between the amount of energy that gets converted into electricity and the amount of energy we have to condense. And what do we do in these? So again, it's kind of startling to look at that. These power plants are only about 30, 32, maybe 35% efficient. Which is to say of the energy that comes in, only 35 to 80, 81 megawatts coming in. We're able to actually get 27 megawatts out on the grid, on the wires going out to the communities, and the rest of it, this 53 megawatts, has to be dissipated. We got to get rid of that. Yeah.
Of course, that sounds really horrible, but you might want to mention the theoretical efficiency.
Yeah.
Based on thermodynamics.
Yeah, based on, and if you look. Thought back to the first diagram I showed, yeah, it's could get improved some, but theoretically, we're not going to get a lot better with this process. We're kind of up against put a lot of investment into superheated, high temperature boilers and really good turbines, but we're really kind of up against the theoretical. You can't do a whole lot better with a Rankine cycle. And so the point of this really was to demonstrate that the way we get rid of this heat is by evaporating water. So there's this nexus between the energy in, the energy out, and the amount of water it takes to drive this process. So we've been talking about coal, but the biggest single power plant in Arizona is Palo Verde. So this is a nuclear plant, and instead of that being 81 megawatts of coal, this is 4,000 megawatts being generated by nuclear reaction within the pressure vessels here. But it's the same kind of process. Now, on a typical coal plant, at least in Arizona, it takes 480 gallons of water per megawatt to make electricity. That's kind of the metric that you use, something like that. And some of them are a little better, one a little worse. On a nuclear plant, that number is more like 700. Actually takes more water at Palo Verde than it does in a coal plant. And that has a lot to do with the zero discharge requirements for Palo Verde and all of the safety things. There's a lot more cooling going on that ends up evaporating water. I always thought this was cool because when you drive by the thing, this just looks so huge. You know, they look at the size of these plumes. This is the water energy nexus, you know, visual that you'd say, this is what it is. However, when you get out, like if you're over on the freeway, far enough away, these kind of get small in comparison to the overall horizon. And sometimes this moisture condenses into a sort of a little cloud. And there's times I've driven by where the sky is blue everywhere, and there's this one little puffy cloud right over Palo Verde, which kind of says, well, maybe that isn't a lot of water. You know, compared to today with the huge clouds we have above us, from a sense of scale, this doesn't seem like a lot of water. But it is a lot of water. And the water here is not being pulled out of the ground, or it's not surface water, it's not groundwater, it's reclaimed water from the city of Phoenix. So this is the tertiary treatment, all of the sewage flow from a large portion of Phoenix, not all, but a large portion of that goes through a reclamation plant and gets pumped and by gravity comes out to the plant here. So this is, in some ways, a good thing. It takes a lot of water, but we're actually reusing an otherwise potentially wasted resource to do it. Okay, now I'll talk a little about water. This, and some of these graphics are a bit old. This is 2012, but this is a graphic of the Colorado Basin, which you folks are probably more familiar with this than I, but really the way I think of this is the boundary here is where all the precipitation, the snowfall, the rainfall over the course of a year basically stays within these bounds. That's what a watershed means. And what you see here, these dots, the blue dots are coal-fired plants. The green dots are natural gas plants. That's Palo Verde, the one big red dot. I don't have solar installations on here. And if I did that this year or last year, you'd see a fairly high concentration. So the sort of the size of the dots for solar, particularly in this area, near the California border, some over here near the New Mexico border would be pretty significant. In fact, there's enough, if you just looked on a peak demand basis, Palo Verde is 3,500 megawatts. There's every bit of 3,500 megawatts of installed flat plate PV in this area of the country here. So from the standpoint of scale, it's kind of impressive to look at what has happened over the last few years in terms of investment in infrastructure to put flat plate out there. You'll notice that most of these dots are adjacent to a waterway here, so there's definitely a correlation. In order to have a power plant, you got to have a source of water. Springerville, which is down here, is actually not on a river, the Little Colorado, but it draws water out of the ground, and I assume there's some relationship between the aquifer and the river. Yeah, big Sulphur Springs power plant down here by Wilcox. I think that's groundwater. Pulling out groundwater to evaporate to make electricity. Let's see, I do want to talk a little about natural gas, and this maybe goes a little to the gentleman's point. Something has happened in natural gas power production in the last, well, probably 50 years, but we've started to see it really get implemented in the last 5 or 10 years, which is combined cycle natural gas plants. So a combined cycle plant takes that, well, first of all, it has basically a jet engine, burns natural gas. The jet engine, the shaft of that's turning a generator. But the waste heat for the 1,000-degree air that gets blown out the back end of the jet engine then gets routed into the boiler for the Rankine cycle that we just talked about here. So we're using both a Brayton cycle, natural gas cycle, to directly create electricity from natural gas. Then we're taking the waste heat from that natural gas process, putting in a boiler, and then running a Rankine cycle. As a result, the water use intensity of natural gas, combined cycle natural gas plant, is about 200 gallons a megawatt. So there's a substantial reduction in the water intensity of electricity made with combined cycle. Now, the reason that combined cycles become very popular here as an investment for somebody like Tucson Electric Power, APS. Doesn't have anything to do with water. It really has to do with the fact that natural gas got real cheap compared to coal. And the natural gas combined cycle plant, although it's fairly complicated, is a lot easier to operate than coal. So there's a lot of cost benefit to that. Yeah.
Can you say something about the relative ramp rates of different kinds of natural gas plants?
Sure. Now there's in general, it's easier to ramp one of these up than a coal or a nuclear. I mean, in general, the problem with those two ways of creating electricity is kind of their thermal mass. Very slow, cumbrous process to get them to build up power or to back off power. Natural gas plants have a much better reaction time. The combined cycle plants I'm talking about still have a fairly high thermal mass and probably can ramp over the time scale of an hour or so from 0 to full output. There are other much quicker acting natural gas devices, internal combustion engines like they're putting in down by Alvernon here, are very fast acting on the order of minutes. So that's another key point to natural gas is it's able to respond to the variability of the output of solar and wind. That is a technical solution to the problem that those two resources aren't rock solid. Another reason we're seeing more. Yeah.
Can you say something about where the natural gas is coming from?
The natural gas comes from the pipelines.
I knew that.
And the pipelines run, across the middle of the state. So I mean, ultimately, I couldn't really tell you where our gas comes from. The El Paso line, from which much of southern Arizona draws, does connect from California to El Paso. So there's many gas fields that are feeding this.
But not in Arizona.
Not so much in Arizona. New Mexico has a lot of natural gas output, but I guess it's a very good question. I don't know the answer to. I don't. I think the natural gas grid is such that gas production in the region has an immediate impact on us. We're able to pump gas very quickly. Whereas with coal, it was a much more laborious process and a lot more involved in it.
I just drove through very large oil and gas fields in West Texas and East New Mexico.
Yeah.
For Christmas. Just thousands and
So a lot
thousands
of
of
it.
wells.
I just wasn't sure, which side it was coming from at this point. I thought it was mostly coming from Texas to Arizona into California.
Seems
What's
likely.
new is that there's been a lot of new production out of eastern New Mexico recently. There was, what we think of as big fields in Texas are now exist in East New Mexico.
Yeah. No, you're right. And I should mention that where I talked about natural gas being much better from a water use intensity, 200 gallons a megawatt hour, that's not considering the amount of embedded water it takes to release shale gas. So the hydraulic fracking process itself is very water intensive. And I think politically in New Mexico, that's as much of an issue as anything with these new gas fields is what's it doing to our aquifers to pump this water out in order to frack the gas.
Okay.
And I mean, it'd be interesting to kind of know what that metric is. How many gallons per megawatt natural gas once you factor that?
And I read an article this morning talking about how the wastewater is really becoming a problem because when you inject it, which is the normal solution now, you then cause aquifer problems.
Sure.
And if you don't inject it, you cause water quality problems in the surface.
Yeah.
Water.
Yeah. Okay, so that's sort of a picture from a few years back of where the power plants are and sort of the distribution of conventional central station power in our area, in the Colorado Basin.
So just a quick question.
Yeah.
Henry. So from all of this that you see and you folks as the experts, what would be like the biggest problem that is needed to be solved from this visual description, if any? Like, I'm sure everything's running smoothly, but maybe behind the scenes this is something that the folks here in the community need solving with certain stakeholders that is yet to be solved. Is there something pressing that needs to be?
How about climate change?
Is that part of this?
Yeah, and I think the investments our utility are making have a lot to do with it. Many of these coal plants are quite old. They were built in the 50s and 60s. They're in need of repair. not really meeting current environmental regulations. The utility has options for how it can solve those problems, and pushing them, I mean, I see this as a big issue, is pushing the utility to think beyond near-term economics and think about what's the long-term climate change responsive solution, rather than what can we do now to generate value to the stockholders. Anybody else got that?
And they just, in the current rate case, they're buying another natural gas unit in addition to the rice plants that they're currently building. So they're still currently investing in more fossil resources.
Yeah. Okay, so I'm sure you've seen this, the sort of apportionment of the Colorado River, this main vein that runs through the region here. This is the main water source, the main input that we have, certainly in the lower basin, and how it's apportioned. There's the thing that always bugged me. If you look at where the basin boundary is, there's this little sliver of California. You know, they're in there. Yeah, they're entitled to some of this, but got 27% of the total. That was politics at work. Colorado gets 23%. So here, this is maybe what intrigued me about water people, is they got Sankey diagrams too. So this is a Sankey diagram of how the water in the river from Lake Mead down is splits. And this is sort of the, you know, the regulations allow. So here's close to 10 million acre feet. Arizona gets 2.8 of it, much of it through the CAP. There's Nevada. This is mostly Las Vegas, is fed from here, 200,000. Here's the California chunk. Gets split out through a number of different canals and piping systems. Much of it going to the Central Valley, and the rest of it going to the big metropolitan areas in Los Angeles and San Diego. And here's Mexico, who still gets some water. 100 years ago, I don't know if it was all of it, but most of that went down into Mexico, but it's been distributed out. Here's our situation. So we're on this, and this is really, as far as I can tell, I don't know if only is the right word, but almost our only water source. It comes through the CAP and down to Tucson. Is that accurate to say we're pretty much CAP at this point?
In Tucson.
Yeah.
Yeah.
Yeah,
But
we have no
not
other.
surrounding areas, and there's a lot of.
Yeah.
But,
Yeah.
yeah.
Okay. Okay. Then the sources on the Arizona as a whole, 39% is river water from the Colorado, 19 from surface. When you look at Phoenix, huge metropolitan area, about half of its water is CAP, and the other half is surface water. Some split like that. Yeah. Yeah, but we're almost entire. I mean, this to us is absolutely critical. This is our future depends on that piece. So here's another Sankey diagram that I think really shows the embedded energy in water. You know, this water that we're relying on, the piece that comes to Tucson, all of our water is pumped uphill. These are gravity open channels with pumping stations. So we have a big pumping station at Lake Havasu, Mark Wilmer Station, humongous megawatt scale pumps. And in fact, I think there's something on the order of 20 megawatts of electric energy gets converted into pumping energy to push the water uphill. Then it drains down a channel, gets pumped up again, And so you can really imagine how critical it is for our water that the electric energy flows to the system. We don't have electric energy, this thing flows backwards or peters out, or this is a river running backwards. The other thing that's interesting about this is the scale of these lines reflects the total amount of water in the canal. So you can really see how the water drops off. Here's, of course, you know, the Phoenix area, and then you can see it kind of drop off here. Much of this is to ag. I mean, most of it is. There is some evaporation, which is always a question, but on an annualized net basis, it's something less than 10%, 5-7% of the water that gets pushed into the system evaporates out. And then this graph, which again is a few years old, but I think it's still accurate, is kind of startling to me as a mechanical engineer, thinking how important water is to what I do. In reality, I'm sort of playing in the industrial and municipal area here. Some small piece of buildings are in here and maybe power plants are in industrial, but the big chunk of water in Arizona goes to ag, which is always a little surprising. If you drive around the state, it doesn't really seem like there's that much ag. You fly over Phoenix and you can see the big fields in Maricopa on either side. And Yuma takes a lot of water. It's a fairly intensive process. Doesn't take a lot of land area to end up soaking up 70% of the total state's water. So again, if I were really attacking what are the fundamental root things we should be addressing if we want to solve the water problem, ag is certainly one of them. Are there ways to reduce that?
Well, of course, now you combine CAP, surface, and.
Oh, sure.
Yeah.
Yeah, I'm sorry. Yeah, that's absolutely true. Yeah, this was just the overall image of how, but you're right. And really what I should be looking at is take CAP and describe that in terms of industrial, because CAP doesn't really feed many power plants directly. There's not a lot of, power plants running on CAP. They'd be very small scale. But it does feed much of this municipal. Okay, now I'm going to talk about air conditioning. And here's a Google image of downtown Tucson. So here's the community center. And here's Bank of America building, HEMA Government Center. And I'm really using this as a kind of an example of an energy district. For some years, well, we have been involved in the air conditioning plant that runs the Tucson Community Center. So there's a fairly large plant in here, which takes water, uses water in cooling towers for projecting the heat of refrigeration machines. There's another similarly sized plant that serves all of the government buildings. The Bank of America building, Bank of America, this building, legal services, library. If you were just to look at the sort of thermal signature of downtown, you'd see that almost all of the large buildings are using cooling towers for rejecting the heat out of the buildings. One of the things that we've looked at under contract to the city, but also just thinking might be a good idea, is the idea of consolidating a single cooling district here, having one network of pipes that cools the entire downtown and involves some very efficient equipment and thermal storage, thermal energy storage, and perhaps a different use of reclaimed water for ultimately rejecting the heat. Haven't been able to sell that idea to very many people, so we still have many individual operations, many of which are not particularly well maintained, not very efficient, and particularly on the water side, kind of wasteful. That idea, district energy for downtown Tucson, really, there are many places around the world that employ this idea to great advantage. So across the US, Austin, Texas has a great big downtown cooling system that's quite efficient. San Diego has one.
So how does that work? There's one cooling system and then the cool air is piped into a variety of buildings?
It's actually cool water. So and that's the way these work. So we chill water down to 42 degrees, pump the 42-degree chilled water to buildings, and then it goes through coils, radiators within the building air handling systems to extract the heat. Yeah.
So one of my concerns about district heating systems has been that they're usually powered by fossil gas.
Mm-hmm.
What about the district cooling system? Are they electrified or are they
Yes.
fossil?
Yeah, basically they are electric vapor compression machines. So they're big compressors run with a refrigerant running through them, running on electricity. Yes. So that's a good point. We're seeing a great change in district energy from these sort of fossil generated heating sources to heat pumps and electric methods of increasing the performance of converting electricity into heat. I've been involved in this district energy idea for most of my career. I'm a member of the International District Energy Association. I had an opportunity to go to Dubai a few years ago, which is a huge city built in the last 15 years. which is entirely operated on district cooling. So there's a million tons of district cooling in Dubai, which by scale is just tremendous. But I think one of the reasons I became interested in this sort of energy, water, air conditioning topic was looking at how they handle the water being extremely important to the Emirates and the Gulf in general. And they've run all of these central, absolutely essential cooling systems off of reclaimed water. So their basic premise is you draw seawater out of the Gulf, run it through a desalination process, make fresh water, pump the fresh water to the city, serve the building needs, but not the cooling needs, just the building needs, drain the water back to the sewage plant, can treat it enough that you can pump it back to the city for use in the cooling towers. And then from there, most of it evaporates, some of it gets blown back out to the sea as a sort of concentrated blowdown. So that's sort of the overall water cycle in a very arid, very hot place. Much hotter than it is here, more arid than it is here, but as an example of what you got to do to live in a place like that. So here's a Sankey diagram that kind of shows the energy flow in a city. Here's my little city here. And what we normally think of as air conditioning, sure, a lot of it is the envelope. This is based on, kind of an energy model of downtown Tucson. If you just looked at how the energy flows through the downtown on a hot day, this is the proportion that's coming through the windows and the roofs and the walls. This is the proportion that's coming through the ventilation systems, the fresh air that has to be injected into the building where you got to cool that down, bring the moisture out of it. That's the loads that you get from the people themselves, the sensible and latent loads. And this red is the amount of internal energy that's being added. This is the elevators, the computers, the lights, the plug loads. And it's roughly half of the total amount of energy we have to extract out of the building to hold the temperature where we want it. Roughly half of it is electricity. So as time goes on, we get more efficient appliances, people have better occupancy, sensors and controls. There's a lot you can do to improve that little thing. At any rate, all these add up, and this is the energy that we just talked about that has to be extracted from the building, sucked out of the building in order to keep the temperature where people are comfortable, which is 72 or 74. That's done in the air handling system. And in order to actually pull the energy out in the air handler, you've got to have a refrigeration machine. This is how that works. And the refrigeration machine involves that much energy here, sort of proportionally. Again, you get all this, you collect all this energy, you now gathered it all together, you got to get rid of it. And how do we typically get rid of it? Is through a cooling tower, which is consuming water. This is another example would be the University of Arizona. Very large district here, 12 million square feet of buildings, all of which are air conditioned through a system not unlike this. There's actually 3 of these plants scattered around campus, but we're extracting all the energy, running it through cooling towers. And one of the things that's kind of interesting about the U of A, if you look on an annual basis, half of the water the U of A consumes, 50% of the water is being consumed in the cooling tower. So the other 50% is the showers and the faucets and the toilet flushing and the student union and, the gym, whatever. But the other 50% is what it takes to cool the campus. A fact that you don't really get a sense of wandering through campus. You go in the building and nice and cool. Hey, that's nice. Didn't realize that was half of our water is going that way. So I couldn't have a presentation without a psychometric chart. This is what I live for. This is the diagram, psychrometric chart. Yeah, this is the diagram that shows sort of the thermodynamic conditions of the ambient air. Along the bottom is the dry bulb temperature. So, we get down to 30s sometimes, as low as this. Oh, the scatter diagram here, the color gives you an idea of how many hours there are a year. So there's a lot of hours a year in this region of the chart where it's 55 and very dry. There's fewer hours as you go out to the edges, but this is our summer design point. This is what we design air conditioning systems to. And we've occasionally seen temperatures and humidities higher than that. I failed to say this is the vertical axis here is a measure of the moisture in the air. So the humidity level builds up as you move up this chart. one of the reasons we all live in Tucson is because we have so many hours where the humidity is low and the temperature is reasonable. You know, the temperature's in the 90s, humidity's quite dry. So we have such a big band, lots of hours grouped around here. Sure, when the monsoons hit, we're up in this region here, it still remains relatively hot, but lots of moisture. This little diagram in the middle of the box kind of gives you an idea of humans typically are happy, productive, not complaining about the temperature when we're in this region here. You get much outside this region, people are going to start to, it's too hot, it's too cold, it's sticky, human nature. But there's physiological, real scientific reasons why it's harder to dissipate heat when you have wetter, hotter conditions. I talked a little about Dubai. If you looked at the psychrometric chart for Dubai, translate this up to the sort of the top quadrant here, it's very hot, very humid all the time. So we're not too bad. But nevertheless, 50% of our water at the university is going to air conditioning because of the hours that are beyond the comfort zone. All right, so because of this, I just want to talk about 3 ways we typically air condition buildings here. This, of course, is the swamp cooler. This is, if you've been here a while, this used to be the normal way you had air conditioning in your house. You had a swamp cooler on the roof, and you were probably happy with that. When it first fires up, very dry conditions in April, May, June, put in brand new aspen pads, turn this thing on, oh, it's just beautiful. It's making really cold air and it smells like aspen, beautiful. Wait till August after you've run it for 3 or 4 months. Now the humidity levels are up here. It's not capable of making that kind of cold temperature anymore. So now it's kind of sticky, warm, and probably stinky air. And people aren't real happy with that. So what has happened really over the last 20 years is the city has evolved from just about every residence being evap-cooled to just about every residence being a packaged air conditioner using mechanical refrigeration. And that's because in monsoon seasons, we're able to make much cooler air. We're able to hit this comfort zone a lot more regularly. It's dial the thermostat and you can control exactly what your indoor ambient is. In a swamp cooler, not so much. So here's the energy, water, air conditioning nexus in a little nutshell here. Coolers are directly evaporating water into the airstream. So if you wanted to figure out how many gallons it takes per ton of refrigeration, of course, that's a unit we use. A ton is the amount of energy it takes to melt a ton of ice. Arcane unit, but that's what we do. So I did it that way. At any rate, it takes a gallon per 1.5 gallons a ton hour to run an evap cooler. But the energy use is extremely low. All it is a fan that's blowing in here. So we have 0.15 kW per ton of electric energy. This unit, the packaged rooftop air conditioning unit, takes a lot less site water. It has no water. There's no water we're drawing out of our aquifer, out of our pipes to operate this system. But there is some source water. We're using electricity. Therefore, we're going back to a power plant, and that was the 600 or 480 gallons per megawatt hour. Well, that sort of is embodied in the energy we're buying to run our air conditioner. So there is some water involved in using a rooftop air conditioner. Another thing that people don't normally think about, turn on the air conditioner on your roof, you're not really thinking I'm using water somewhere, but it's not an insignificant amount, about 0.5 gallon a ton hour. And if you think about typical house, that's about 5 tons, maybe somewhere between 3 and 5 tons. If you think about running your air conditioner all day long, you know, that's a lot of ton hours, 24 times 3 tons. Times 0.4 gallons. It's a lot of gallons of water. That's more than you're using in your bathtub. Yeah.
An obvious exception to this is solar, and you capture the condensate into your gray water system.
Right.
Your net water producer.
Okay, so I'm getting some, yeah, I'm getting there. So hang on. Okay, so then we look at the third option, which is sort of the district option. This is cooling towers. These are the things that the University of Arizona has, large cooling towers. All of those buildings I pointed to in downtown Tucson have large cooling towers. And the main reason to do it this way, it saves a whole lot on electricity. The motivating reason to go to water-cooled air conditioning is 30% reduction in the electricity. So if you're thinking about this from a cost standpoint and electricity is expensive, that's a big deal from an economic standpoint. If you're thinking about this from a carbon standpoint, that's a 30% reduction in whatever carbon was embedded in the power grid. Now, certainly as the power grid evolves, that becomes less and less significant, but that's the motivating thing. But here's the thing that's really startling, is the total amount of site water, 2 gallons per ton hour. And this is why 50% of the university's water goes up the cooling towers. It's a pretty water intensive process here that I don't think people really recognize that. And a large reason why people don't recognize that is the price of water is so cheap. This is not a very significant, this does not translate into a big number on your bill. And when you compare this number to your electric bill, you'd say, hey, I'll spend more water to get my electric bill to go down. Okay, so now my final 2 slides here. So this is the overall, tried to put the whole picture together here on this slide. Hopefully you can see that. This is kind of the conventional way of doing a district energy system. This could be downtown Tucson, this could be the University of Arizona, this could be anywhere where you've got kind of a low density, enough people, enough occupancy, enough internal kind of equipment loads that it makes sense to put in an air conditioning system. So here's the power plant. Back at the power plant, we're using some kind of a fuel source, kind of poorly, but you know, we're meeting about as good as we can do from a thermodynamic standpoint, but we're getting 30% of that, turning it into electricity. The rest of it we're wasting, which results in the water use at the power plant. That's that line. Some of this power then goes back to feed the pumps in the plant. So this kind of represents the CAP here. There's the relative magnitude of the line of evaporation from the CAP. So on net, it's like, well, that's not that significant. 5% of a big number is a big number though. Here's the grid. There's some losses in the grid, you know, transmission losses, that sort of thing. And you get up into the district, and there's a kind of thing we saw as a blow up before. So if the entire district were air cooled, if everybody had a packaged unit, nobody was connected to the water, you'd see this kind of scenario here, 27.8 cubic feet in this graphic going to the district. And that's largely going into buildings for hygiene reasons, you know, sanitary sewer kind of reasons, but there's some other process loads. Most of it though, going to showers and toilets and sinks and things like that, which means it then comes back out. There's some losses in the wastewater system. We don't recover all the water that goes to the urban core. Some of it goes away one way or another. The rest of it comes back to the sewer plant. So this diagram then shows how this scenario would be in a water cooled system. And again, you just look at this, we've saved a fair amount of electricity here. This was 81. We went from 99 megawatts to cool this whole district down to 81 megawatts. So we're using substantially 20% less electricity, which is a pretty major improvement. But we've increased the water demand by 25% or more like 50%. So that's what we've kind of have at our hands now. This is a good example of how a conventional district cooling system works in Arizona. A lot of water going into the air conditioning process in a way that people don't really recognize or think about.
Did you say it increases the water use by 50%?
Well, we went from 50 to 75 to 80. So
Okay.
what is that ratio?
Okay.
That's more like, yeah,
Yeah.
50%. Yeah. So I guess just to kind of talk about where we could go from here, opportunities. One of the things that's really obvious as you think about this is conservation in the buildings. That's this piece here. That's reducing the demand. I mean, if you had your overall hierarchy of things you ought to do, if you only could do them and had the money to do them, that seemed like a really good first target. Drop these numbers, drop the amount of electricity it takes to operate your building. Make it so the envelope doesn't suck up so much heat in the middle of summertime. Collapse all these things. This is sort of the lead approach. What a really good building ought to be able to really reduce this, and it has this multiplying effect. You reduce energy use here, you're going to be reducing the site energy and water use, as well as ultimately the source energy and water use. The next thing is the idea of using reclaimed water in cooling towers, which is sort of what we talked about with Palo Verde, except taking we have a reclaimed water system that's capable of being evaporated into the airstream with some minor considerations. You can take reclaimed water out of our system and pipe it into your cooling tower. And that, to me, seems like a very logical kind of a thing. This would be following the example of the Middle East, other places that are very water stressed. Rather than using reclaimed water in watering golf courses and parks, take that water and use it to benefit in air conditioning.
I understand TEP uses mostly pristine groundwater.
They do indeed, yeah. They are pumping water at the plant here at any rate. And then the third thing, which makes, I think, this is probably these are more like systemic things. These are the things you could do that solve existing problems. A third thing you can do is say, all right, well, let's get off of coal and natural gas and put in a lot more solar. Put in enough solar that we really could use air-cooled chilling rather than water-cooled chilling. So it's going to take more electricity per ton. But if we have enough PV and we have enough thermal storage to go with that, or battery storage to go with that, where you're capable of using it across the day, then this is a long-term solution that both reduces the carbon footprint as well as addresses, to a large extent, this portion of the water problem that we face. Okay, that's it.
Yeah.
Great. Any start of the discussion?
Yeah.
So I've never seen anything about using condensate water as potable water.
Sure.
Are there health and safety issues there I don't know about?
Let me go back to the psychometric chart. Certainly there are some regulatory problems there. So it would be hard to get condensate water approved as a drinking water source. Condensate water fundamentally is distilled water, but it unfortunately goes through pipes, and the coils themselves, it's not virgin water. It's been contaminated. So as a drinking water source, probably introduces some problems with regulation. One place we've seen great success is taking coil condensate water and putting it in as makeup to a cooling tower. So there's a number of university campuses which have a pipe from all of the buildings to collect coil condensate, route it back to the central plant, and pour it into the basin of the cooling tower, which requires no regulatory issues, quite easy to do. One of the, we talked about the advantage of living in Tucson, how dry it is and how few hours we have where the moisture is high. The bad part about that is we have a very limited period of time when coils condense. So the period of time when we can actually collect condensate is pretty much limited to July, August, half of September. And so when you look at the volume you can acquire from doing that, and we've done this study at the university a couple of different ways. Certainly during monsoons, there's a great potential. A lot of water we're draining down the drain because we don't have anywhere else to put it. But when you look at that on the overall magnitude of that water compared to the amount of water we use on net, it's a very small number, and it's a very high capital cost to run the piping system.
So I have a question about ENR2.
Yeah.
Can you talk a little bit about what the level of conservation and level of how you ended up cooling that building and how the university reacted to that? What kind of negotiations went through?
Well, I don't know that negotiation is the right word. There was a great desire from the planning, design, and construction folks. Well, but really it was coming from the users. The name of the building, these were environmental, natural resource people, very motivated to make a low energy and water building. So we picked what seemed to be kind of best of class ideas and pursue those. We looked at a number of different alternatives of one type of system versus another, and we came to well, here's a system that looks like it's going to have a long life and be low maintenance as well as being high efficiency. Yeah, again, it wasn't so much negotiation as the problem in construction anywhere with anything is cost. So you drive, here's our goal, we're gonna achieve these energy targets, but here's the dollar value, and we don't have a dime more than this amount of money. And so the challenge for the designer is to come up with a compromise that gets us the best energy and water use for the limited funds we've got available. And there's a lot of compromise for the users there. One of the things is that building's temperature control has a much wider band than most university buildings. The way it's set up in wintertime, it's cooler than most buildings on campus, and in summertime it's warmer and it floats. We aren't so precise putting a lot of energy in to hold the temperature at exactly some set point.
Interesting.
That's a big deal. Yeah.
That's true in this building, but I don't think it's intentional.
Yeah.
We also have a question there,
The second question I had on the psychometric.
Yeah.
and we'll get you on the webinar as well next.
That little comfort zone band in the middle, do you know if that was for humans throughout the entire planet, or is that more specific to Americans with a very narrow range of comfort?
That's a great question, because I have seen studies where in India, so the basic idea, there has been a fair amount of research on how humans behave under various temperature and humidity conditions and with various levels of clothing, and also dependent on their activities. What kind of activities are they doing? So there's a lot of parameters in there. I think the work is mostly Northern Europe and the US. I mean, I think the study was based on those people, because I think in India, it has been sort of, back-figured that people are capable of working in offices at much higher temperatures in the 80s with similar productivity. So this goes to a question I've had. I mean, I was born in 1956, and that was sort of the beginning of modern air conditioning in office buildings. And now, over the course of my life as an air conditioning engineer, I would say the population of the US has become much more discriminating and demanding about air conditioning, much less willing to put up with wider temperature and humidity swings than what were common when I was a kid. I don't know if that resonates, but my dad didn't have air conditioning in his car. I mean, yeah, and it was okay. It was just, driving in the car, it's going to be hot, roll down the windows. But now you got to have it.
Except in movie theaters in Tucson in the summertime, you still have to bring your jacket.
That's true. Then we have a question online, which
Yeah.
is what level of wastewater treatment is required to use it for cooling?
Okay, so this would certainly be dependent on the wastewater water quality. I think when we look at the water quality of our wastewater, we would pay much attention to algicide, so there would be some treatment for biological control. One of the problems we have in Tucson with our water, our CAP water, is a high mineral concentration. So we have high calcium and, probably more importantly, high silica levels in our water, which, as we evaporate water through a cooling tower, that concentrates the residual in the basin. And the problem with silica is it plates out on the heat exchangers for the big chillers, making them less efficient. So in order to keep the efficiency up, you've got to control the silica. And to control the silica, you blow down water. You're wasting some of this water stream in order to keep the silica down. There's no known methods, chemical methods, to extract silica from our wastewater. So it's an interesting challenge here. Elsewhere, where there are water streams that don't have calcium and silica, there's a lot less water waste. We're kind of forced to waste water here because of those two things.
Interesting. And there's one more question, and then we have more here.
Oh.
Oh, and you have one. Do you want to go, Robert?
I do, because I'm afraid of not getting it in. Well, you mentioned briefly, I got a few questions. You mentioned briefly loss of lines. Is it?
Yeah.
So what would it take that 30% figure to, you know, of a fossil fuel power plant to, transmit the transmission lines a few hundred miles, or
Yeah.
another 5%, or is another like 3%?
So this depends on how much demand is on the line. It's current loss. So on a really hot day when everybody's running their rooftop air conditioner and we have the highest loads, then the wires become relatively undersized and there's more and more loss. So you got to be careful about the line losses. It's real dependent on how much juice is flowing through them. Here in Arizona, we actually, our utility has kind of oversized our line. So you don't hear a lot about high line losses in our grid here. And I'm guessing we're on the order of, on a hot day, 3-5% of energy that is from the point at which it was generated at the power plant to the point at which you use it is lost. On the East Coast, where there's lots of constraints on the grid, I've seen numbers as high as 15% on a hot day is being wasted through heat just getting from the plant to the end uses. So it's kind of a hard question, and I think TEP and APS have in general put in ample size lines with the anticipation of substantial growth in Arizona. So hey, this state is growing, and we want to put in 40-year lines. Let's oversize the bejeebus out of them so we got plenty of ability to serve these loads later when they develop.
It just costs more to build the infrastructure.
Yeah, and right.
Now, you mentioned mini splits, which I see are terribly efficient. I see them all over.
Yeah, no, it's a form of air-cooled chilling. I showed the sort of packaged rooftop, but it's the same basic technology. And really has the same thermodynamic ability there. So it's got the same kind of performance. The efficiency of one of those, kind of like this line loss thing, is entirely dependent on what the ambient temperature is. Hotter it gets, the less efficient the mini split gets. So sure, it can be really good on a 65-degree day. It's a very efficient little operation. On a 110-degree day, it's consuming a lot of amps for the amount of tons it's putting out.
And something else, the footprint of the various methods of generation of electricity. I mean, it seems like solar on the roof, which power and a mini split on the roof. Of course, the solar panels provide shade on that roof, which cools the house a bit. It's the sun shines during the hottest part of the day. It seems like that's just like the bare bones most efficient way to operate. Is it?
Yeah. Well, I think it depends on your viewpoint. If you're looking at a house, one house, the control boundary is the yard. Here's my property line.
Yeah.
That may be true. That putting the solar on the roof, a little battery pack, having a controller and paying a lot of attention, that may be of the best life cycle cost way to do it. If you look at a district like downtown Tucson, there probably isn't enough roof area to be able to actually accommodate the load. And then you get to the TEP argument that it is much more cost effective and to some extent efficient to build utility scale solar systems on the megawatt or gigawatt size, where you've taken a large piece of land, graded it off, sort of optimized it, and then completely populated it with solar panels. The trade-off then, of course, you've got some line losses to get it to the loads. But yeah, all right. Well, so I mean, it's a different kind of a calculus to get there. I talked before about, and I have a slide, but I didn't show it. One of the, we now have a lot of megawatts of solar power in the most sun-intensive parts of the state. So on the west side of the state, there are a number of gigawatt scale power plants. When you Google Earth those, and it's an interesting little exercise, take one of those power stations, Google Earth it, you have to zoom way in. It's the size, it doesn't take that much land. It's not like we're consuming, 10 10% of the available real estate, where it's a small piece of land to generate a gigawatt of solar power. So sure, there's habitat loss, there's a number of problems with it. But you got to take that, I mean, I think you just got to calculate that in the overall mix. And I just want to go back to it's a little different situation if you're just looking at a house as a discrete individual entity ecosystem, and compare that. It's a different story when you look at a city as a whole or an urban core as a whole.
We have one more and then we'll
Yeah.
wrapping up unless we have something to help. Some person has a burning question. So do the energy use in current slide include energy used for water treatment used on the site or
Yeah.
the power plant?
Well, the idea was this is the site, this is Tucson, this is the local, there's a water tap. So on the case of an evaporative cooler, there's a pipe that goes from your water meter up to the roof. And that's what's taking a gallon and a half. The source water, 0.07 gallons per ton hour, reflects the water that's embedded in the electricity it takes to run that fan. So I think that's the question here. The total right here, 1.57, is the addition of what we're using from our local source, our water meter, plus what's embedded in the power stream. That's the total. And this is the number for water cooled chilling, 2.26 is 2 coming out of the or coming out of TEP if we're doing it here. I'm sorry, coming out of CAP, plus the 0.26, which would be back at TEP's power plants. Gets you that.
Okay.
Yeah.
Yes, one more burning question or comment.
Comment was just that I wanted to point out that there's a huge resiliency difference between distributed solar and utility scale solar as well. When you have the solar and battery on your house and the grid goes down, you can still do most things. There's a couple million people in California that would love to have that instead of grid power, because their grid power goes out for several days.
That's a good point.
Right, let's,
All right, thank you, yeah.
And you're welcome to come and have a chat again afterwards. I have to take off because I have a webinar.
All right,
I'm
very good.
already
Yeah.
missing, but it was
Sorry.
wonderful.